Thank you. My name is Alexandr Notchenko. I'm from Moscow, and I represent, well, I'm not sure if I represent like several parties in here. Skaltech Institute of Science and Technology, and our data science community from Moscow. I'm going to be talking about work that we did in the last summer and presented it in a 3D deep learning workshop at NIPS 2016. It concerns analyzing 3D shapes, but later on we discovered that it might be useful for other applications as well. So, start from first point. 3D shapes can be, and 3D objects can be encoded in multiple ways. Usually it's meshes, triangular or other kinds of meshes, point clouds, just some amount of points in a frame of reference, implicit surfaces and potentials that are more obscure method of describing objects. Voxels are quite popular, and some people use multiple projections to several perspectives to represent object, but that's, of course, not completely 3D. So first three, really hard to fit into neural network because of their irregular size. They have a spatial nature, which usually is better processed by convolutional neural network, but they have variable size a lot of times, so it's not obvious how you put this data inside a network. And voxels and 2D projections are possible spatial representations of objects to put them into neural networks. But for the 2D projections, there is a problem that bodies with surfaces have a bad property of being self-occluded. So if they are not transparent, you cannot see what is inside of the volumetric bodies. So it only leaves us with the voxels, which have their downside as well. They don't encode smooth surfaces as well. For example, we had a data set ModelNet 40. It's a benchmark in shape classification and shape retrieval tasks. And we encoded different mesh objects into voxels with different resolutions. And you can see they get more detailed with more resolution that you apply. But for some objects, it's quite obvious even at the low resolution of 30 by 30 by 30. But if you have a much bigger data set of objects, it might be more difficult to discriminate between them. And also, like another kind of objects that we want to analyze, it's biomedical imaging data. For example, on the left, you see MRI images of brain with a lot of skull and other stuff cut off. And you can see it's quite sparse. And on the right, we have computer tomography images of prostate cancer patients. And you can see a lot of blue on those images. And blue means lower values, lower densities. And if you use some thresholding, you can turn most of those images into zeros, so effectively making them sparse. So the idea of using convolutional neural networks on sparse data is not absolutely new. Dr. Benjamin Graham from University of Warwick, now he works in Facebook research, in 2015 did a research where he created a special library that uses C++ and CUDA to encode shape meshes of bodies into rectangular or triangular mesh, 3D volumetric meshes and operate on them. There's several not obvious properties. If you, for example, encode a 3D object in a triangular or tetrahedral mesh, this is probably, properly called tetrahedral mesh, it has only 4 different sides adjacent to it. So every tetrahedral voxel only has 4 other ones adjacent. But cubic, like cubes like that, have 6 sides. So effectively, if you have a boundary around some voxels, it's much more efficient to be in a tetrahedral space. But you still can conserve a lot of topological properties of objects. And yeah, he published this research on arXiv and developed this library, but it was really complicated. Not really obvious how to use it besides re-implementing other C++ or CUDA programs on top of that. But that's a skill set that is really not that widespread. Not a lot of people can effectively write CUDA in C++ code. So we developed PySparse.net. It started like as a wrapper around the C++ and CUDA library with all the Python functionality that it needs. But then we added some additional functionality so it would be possible to process volumetric data like biomedical images. And this is also licensed by GPL3, version 3 license. And it uses Cython to effectively wrap C++ and CUDA code into Python. And I'm going to, in more detail, show you how it's done. So yeah, we have some pros why we want to do this. Like the good reason is that we want to have the efficiency of really optimized high-performance library that uses the power of GPU. But also we want to have a simplified interface, Python interface to get properties of interactivity, modularity, debugging, essentially getting a way of looking into neural network so we could debug and diagnose problems more effectively. Also, because if you use some interchangeable format, for example, we're able to train neural network on sparse data, then translate weights of this network to, for example, Keras model, and then use for inference time more popular engine like Keras or something else that can encode convolutional network and have all the efficiency that we want at the inference time. But we also have some drawbacks. Like this framework is absolutely niche framework. It's not general purpose. It's only reasonable to use it when you have volumetric data. Because in other cases, other frameworks work as well, sometimes better. And we have a lot of optimization exactly for this use case. And the code base is pretty complicated. Benjamin Graham, in 2015, applied his library at the data science bowl, first data science bowl at Kaggle competition, and won. So it got a spike in popularity, but people were discouraged because of its complexity. Also, because of implementation details, we right now cannot, we can use special Python language loss functions and whatnot, but it requires you to translate all of the information from GPU to CPU, and it creates a lot of overhead, which you want to avoid if you can. So let's dive into it. I hope not everybody, you can see the code. The size of the letter is appropriate. So on the left, you can see what it looks like, a CUDA and C++ library. It's a header file of one of the modules, and it encodes some class of sparse network. And it has some, like, I'm not a huge expert on C++, but I can understand that we have strongly typed attributes of this object. We have some constructor, some destructor, and some methods that take other typed arguments. If you use Cython, what you can do essentially, if you found optimized effective library, you can re-implement the header files using Cython notation and define PyDX file, and essentially re-implement, well, not re-implement, but describe the signature of a class and signatures of functions in Cython using this special notation where you use cdefs, you identify which classes you use, and you can only describe the parts of the objects, the only ones that you're going to use, not the complete thing. Like, there's a lot of methods out here, but we only need like 3 of those or 4. So you can just describe some of them, the only ones that you need, because only they're going to be accessible in other Cython code. And this is another Cython file, pyx, extension pyx. And we define here an object that's going to be an object, C++ and Python object at the same time, described in Cython notation here. So you can see that it's pretty similar to usual Python, with only distinctions being you add cdefs where you want to describe something which is in a C land or going to be implemented underneath, converted into a C object as well. And you need a couple of special methods. Initialization for the Cython classes done in the following way. You create an initialization object cinit, and you define, actually the type notation here is optional. Cython is completely able to use hints and implicitly convert types. So those typing here is just strictly for optimizing the code that's going to be below. So you create a Cython wrapper object that's going to be accessible in Python, which has these attributes. But this attribute is actually a C object. And we pass Python variables to constructor. And we initialize. New is a special word in C++ that initializes C++ object. We assign it to this attribute, and we provide some functionality around it. Because this code in Cython, essentially, it works in a C land, but it also can be accessed from the Python with by these attributes. Oh, sorry, I mixed up. Like, when you define something as cdef, it's not accessible in Python because it's a hidden C attribute of a Python object. But if you can also define stuff here using usual defs or just Python, just usual Python. For example, you can pass just a plain Python code to the Cython compiler, and it will guess types of the different arguments and can convert your Python code straight to the C code. But if you provide some additional notation, it's going to be much more optimized on a compilation step. Also, you need to provide explicit way to destroy this object. A lot of problems arise when you use Cython. If you have some object, for example, here it's a C object sparse connet, and this object is defined in a C code. So you need explicitly define when it's going to be created and destroyed. Because if you not do that, you're probably going to have some segmentation faults and memory leaks and a lot of other memory problems. So if you don't want to touch C++ very much, you just remember 2 things: to have a correct initialization and dialog that destroys most of the C objects, so they would not take more memory. Oh, sorry. Yeah, so the compilation step works as following. We have the original sparse connet module, which is essentially a bunch of CUDA files, CPP files, and header files. And you can write a binary, write a separate file, and compile it, and it will work. But what we do, we added those Cython additional files, pyxd, which mirrors the definitions in header files that we need, and defines some functionality in pyx file. Then Cython, in the compile time, converts those definitions and payload into a CPP file. Then our make file turns everything into object files, and then using NVIDIA compiler NVCC in a linker mode, we can connect and link it all together into SO shared object, which is essentially going to be a Python module. Yes, so there are some nuance to that. For example, if you define in a setup.py file the compilation steps of all of the C files and create a Cython extension, it's going to be linearized. What I mean by that, it's going to compile each file on its own. It would not be able to compile them in parallel, like JFlag for in make utility does it. So in our implementation, we decided just to compile our Cython object separately, compile object files of sparse.net in parallel using make file, and then we relink them together on a second go. And we get the proper shared object that we can use as a Python module. Another interesting problems, well, not problems, but unexpected behavior is the type assignment. So if you define, for example, this is a class in a PyExa file that describes an sample our 3D shape object, which is described by sparse dictionary. And here, for example, a test. We define in Cython the types of those arguments as numpy and d arrays with types, for example, long and double with some number of dimensions too. So one object is the matrix of indices, which are not 0, and the second vector is the features. What are the values in those non-zero voxels? And we create a C object. We tie it to the file class in our Python module. And here, for example, in the test, you can see its behavior. But the unexpected thing is the types that Cython takes and types that NumPy assumes are different types, and you got to be careful about that. Because, for example, long here means standard int. But double here means NP float. Because there is some type, mapping, you got to be careful with that because it can create some problems in your C functionality. It's the second most important part of when you try to connect Python to C++ is to be careful with type conversions, because it's exactly the place where all the data travels in between C module and Python. Yes, and Cython can do a lot of stuff implicitly. It really has a lot of optimized stuff in it. So for example, if you return a C++ structure, it can automatically detect it and convert it to dict with keys being attributes of the structure. So what we used it for? Initially, we wanted to solve a task of shape retrieval. It means basically to use shapes to be able to search in a library of shapes, like image search, but for 3D objects. And there's a couple of nuances with that. 3D objects can be in some classes. We have a data set that has 40 classes of different kinds of objects, planes and whatnot, which defined by meshes that we convert to voxels and analyze voxels. So this works pretty much like that. We take mesh, pass it through our network, get a feature vector, put it in some spatial index, and then we perform retrieval on the unknown object, on the query object. And we get some number of objects that look the same. So this is a retrieval task. And we use a special case of metric learning. How many of you know about metric learning? Have you heard about it? So it's an idea that you want to learn a representation of your objects such that similar objects are going to be closer together in a vector space, and the more different objects are going to be far away. And you can do this by defining a special loss function for your deep learning task called triplet loss. People working in a face recognition and other types of recognition tasks, when you have a lot of objects of different classes, usually it's better to use metric learning setup. So this triplet learning loss function. What it does, it looks for positive pairs and negative pairs. What it takes some object in the data set as an anchor object. Then it finds a couple of one negative, one positive example. In this case, positive means in the same class, a negative means in other classes. And tries to draw the positive sample closer to itself and the negative sample far away from itself. It's a more stable version of other contrastive loss metric learning. Like when you want to learn a representation, you probably think like the simplest way to do that, just calculate the distance between the same class objects and minimize it and maximize the distance between other classes. Yeah, it would be called contrastive loss. And in that case, there might occur situations when you, in one batch of optimization procedure, you get some objects close together, but then on the next batch, it's going to draw them far away. So they can oscillate without like optimizing the real objective, without finding the proper function that would create a landscape on which, on that landscape, similar would be close and different would be far away. By using separate third anchor object, we can separate them in different directions, essentially creating different areas for different classes. Yeah, the architecture of the network that we use is just plain convolutional deep neural network with max pooling layers in between. It has 17 layers. And you can see from this column, our input is pretty sparse. Well, if it's sparse, we can process it more efficiently. For example, if we render our shape objects in different resolutions, if we, for example, used dense module, something like Keras or Cafe or whatever, those libraries, they only process dense matrices. They have no conception that you might not want to process all of the zeros that occupy the space around the object. But we only do computation that are required. We only compute stuff around the objects, and we don't touch the zero space. So essentially, our input space of this architecture is 160 cube. So we can input any object that can be rendered in voxels less than 168 with a side of 126. So because we don't care about zeros, we can use different architectures. For example, we can have like 30 layers. Our input field would be 300 by 300 by 300. It wouldn't be untractable in a dense network. But because we have no computation of zeros, it might be reasonable to do something like that. And going through this network, when objects activate on different layers, they lose their spatial sparsity and start occupying much more channels. How many of you familiar with like deep learning problems and deep learning methods? Like we already heard a lot of talks on this conference about that. So you can think about this. It tries to convert spatial dimensions into semantic channel dimensions, which represent separate features. And for example, we lose all spatial dimensions up to the last layer, but our channel dimensions would be 192. And our sparsity is 100%. So it means that we have completely dense information. So we started from 0.18% sparse data for the shapes. And for example, MRI data set of brains, it has mean sparsity of 10%. So it means 90% of voxels in the brain images are zeros, so we don't care about them. But when it goes through the network, all of the zeros get compressed, and only the semantic information remains. And the complexity, time complexity, doesn't grow as a cube of input resolution, but grows only linearly or logarithmically, because it only takes information that a sparse image has. So you can see, for example, in this plot, that we had a shape of a car. We had a mesh object that represented a shape of a car. It goes through the network. Some convolutions are performed in it. Then it goes through the pooling layer. Resolution gets smaller. It's now 60. And in 3 layers, it loses half of its dimension, half of its resolution size. So it was 126. Now it's 61 or 62. And we go through the layers until we get just one-dimensional vector, which represents a feature vector of that object. So we evaluated that on some data set, compared it to the other architectures and the methods that people use. This network, for example, is a dense one, and it only uses 30 by 30 by 30 as input resolution. This network uses multiple projections of 3D objects and concatenates them and passes them through several copies of neural network, then assembles feature vectors together and uses them as descriptions. In this network, which uses multiple views as a representation, pretty good actually at retrieval task, because a lot of objects have one projection side where you can have such a projection that would discriminate between classes very effectively. But we are pretty similar. Our performance is comparable to the performance of state-of-the-art methods, and we are much more computationally efficient because we don't do any computation that we don't need to, and we utilize CUDA effectively. So yeah, you can see like on this T-SNE plot, this is we have 192 feature vectors to represent 3D objects. Then we, using T-SNE, we project them to 2D space. And you can see some similarity between objects. For example, here's our like big storage boxes or closets, or here we have doors and wardrobe. Something. And here we have bathtubs and sinks. So it finds common elements in a 3D shape representation. Yeah, we got some conclusions from that. Shape data sets are really, because of their small number of classes, they don't really need big resolution. If you have more voxels, you maybe need to get a deeper network, so the information from the different scale would be integrated better. And our networks actually, better to use them on something that has internal structure, something that has uneven internal structure like medical imaging data, which I showed previously. Because, for example, when you encode a shape, a mesh, into a voxel form, it doesn't really care what is inside of that. It actually works only on the surface of the object. So why are we spending all of this computational power to process something that is not really affecting the discrimination or representation? So it might be more efficient for dense, well, not dense, sparse data, which has internal structure, like organs or brains. Yes, and I wanted also to share like an idea that we had when we trained all this stuff, because we didn't use a lot of cool frameworks that exist now. We had to implement our own hyperparameter optimization scheme. So what we did, we used Google Spreadsheet API, and we wrapped it in a pandas object. So we were able to run several workers, and each worker used Google Spreadsheet as the common object to store the information about experiments. So here, for example, on the left side, we defined all the hyperparameters. On the right side, it constantly updated our metrics when they were computed. And using this column, for example, we wrote that if we want to stop it, we just wrote stop. And when the worker taken this information from the Google Spreadsheet, it stopped or not. So it was an easy and cheap way to use Google Spreadsheet as the coordination server, and also, like, well, not exactly a dashboard, but to collect information about the experiments. So that was pretty interesting as well. So yeah, special thanks to a couple of people who contributed some stuff to the repository. Because it's pretty complicated, we really require a lot of help with experts in C++ and CUDA. And if you have free time, we would be really glad if you can give us a hand. And also, I wanted to say hi from Moscow data science community. Like, it's called Open Data Science. We have a lot of people. And it's probably one of the reasons why Russians win Kaggle competition so much. Because we have some resources only in Russian that where people share information about their approaches, architectures, ideas, and whatnot. So I don't know how Kaggle policy works with that, but that's what it is. And we have, a lot of expertise on all kinds of stuff, and I hope when we're going to have our first PyData event in Moscow, some of you might join us. That would be pretty great. Thank you. How much time for Q&A?
Maybe 5 minutes.
5 minutes, OK.
So can we
Yeah.
Stuff on that?
Probably a question, like you showed accuracy of 90% previously. What kind of data set was it? Like
It was
the data set that what the samples are in?
Oh, samples are different meshes of different objects. There was 40 classes and approximately 12,000 samples. And they were like not really so much diverse. But for example, if you have much more classes, you're probably going to get more benefit from bigger resolutions. So that was some of our findings.
The question is more like 17 layers seems quite a lot for 1200.
We needed to reduce the spatial resolution of the samples, but you can only reduce it using convolutional or pooling layers. And you need to stack them together, so the information flow would be exchange of information from spatial dimension to the feature dimensions would be equal on each step. You cannot just drop in one layer all of the dimension. Mm-hmm. So it probably wouldn't work. Yeah?
We've got a project with the World Seed Bank, and they've got photos of all the seeds there's ever been in all the genetic data. So they want to find relationships between shape and genes.
Oh, really? But is this shape encoded as 2D images or 3D images?
Yeah, and this is what I was wondering. But how does the same technique apply to 2D in that situation?
Metric learning?
Yeah.
Yeah, absolutely. Metric learning can be applied to any setup. If you have a concept of closeness, relationship of similarity and distinction, you can use metric learning. But now there are even better approaches to do metric learning. For example, histogram loss or central loss. So there's a lot of new developments in that field in recent time. We can talk about it later. Any question?
So you had to represent an image in voxels. So sometimes you need to be able to know whether it's a structured mesh. So can you basically go through a mesh and see whether the mesh is out of line, so whether boxes are in line. So when you edit it, sometimes you make it unstructured, and some are programs need to be structured. So can you search through the mesh to look whether basically the boxes are in line?
Well, you can do that, but it's not really required. If we have a pre-processing step of rotating and distorting samples to achieve invariance to those factors. So if they are misaligned, it's not really a problem because it tries to learn concepts that are underneath the voxels. So if the line is you know, like a little bit jittery because it goes diagonally. And if a line is straight, the network will equate those probably. It's not probably going to make a lot of difference. Yes?
Is there a lot of sensitivity to the rotation?
What?
Is there a lot of sensitivity to the rotation, or
Well,
you had a
only if
plane
you
with its wings going up and down, for example?
only if you train it without using those kind of data augmentation. But for example, if you have standard-sized position of things, you can use it without rotation. For example, brain images a lot of times are centered appropriately, so you can use this information without rotations, because every new sample of brain image probably going to be centered and aligned properly. Yes?
So I was wondering if you could give some intuition on what's the difference between sparse convolution and delayed convolution.
Oh, that's interesting. There might be a connection, actually, but no. These convolutions are work the same as they would be in a dense setup, but they are all of the activations going through the network. They not represented as square or cubic grid. They only represented as the dictionaries. And CUDA kernels, what they doing, they operating on a sparse dictionary representation of activations.
Okay. So actually the convolution is a classical convolution.
Yeah, it's pretty old school. But Benjamin Graham actually implemented several different kinds of pooling layers. He has different variants. For example, he invented fractional pooling, and some people describe it to be very advantageous in some setups. Even
So he said it was better to have structure instead of using voxels. So it's sort of like in the brain when you had structure of like a lung or something.
Oh, yeah, of course. No, if you have structured input, it's probably going to learn the structures of it.
Yeah, but how do you represent 3D structure? If you're not going to use voxels, do you use tetrahedron to represent that structure?
I probably didn't get it.
So when you input the data, you want to keep the structure,
Yeah.
but how do you represent that in a 3D graphic? If you're not going to use voxels?
Well, I'm not sure. Maybe, well, we're losing like smooth information, but because we have bodies with volume inside of it, if we provide not just for those meshes, they only had zeros and ones. Ones were occupation of this voxel, and zero was non-occupation. But for biomedical image, in the voxel, we have information about density. So if the information in those non-zero voxels represents some shape, it's gonna learn it. Yeah, we finished?
Yeah. Any questions? We have 4 more minutes.
Yeah, really? Oh, let's answer another one.
Question.
Yeah.
Stupid one. So these voxels, I really shame on you, but I don't know what is it. How do you do normalization, batch normalization, and things like in image recognition they change input images with some different random transformations to make sample bigger and to
Yeah, augmentation.
augmentation.
We can do this augmentation as well by adding some random noise in other sites or flipping some voxels at some places. For example, actually there are some interesting connections. We right now also experimenting with using HAR wavelets to turn 3D images into sparse representation in wavelet space, and then process them. So there exists some interesting wavelet transformation that can turn smooth objects into sparse, and if they are have enough equivalent information, we can learn the same properties. But your question was?
What about normalization?
Oh.
Yeah. How do you do normalization of 3D object? How you subtract mean?
The same way. It's just a tensor. You just calculate the mean and subtract it if you want.
Voxel is like a tensor, like a
Yeah. Well, it's a dictionary. It's only non-zero elements. So any operation on non-zero elements would be the equivalent.
Do you have any visual stuff on input objects and normalized objects?
No, it's just only color would change, right?
Okay.
I mean, like color represents the value in this voxel, So if we normalize stuff, it just changes the color.
Okay, cool.
Yes.
Any of the features that come out, can you see them in the data? So, like, are the features anything you can see in the first image? So, what do the features mean anything, or are they just like?
Oh yeah, of course they mean. We had tested. We found what would be the input. What would be the input image maximizing different outputs of different vectors, and found out it's sometimes look a little bit like 3D harmonic functions. Like when people look at the filters extracted from the network, they sometimes look like Gabor filters or edge filters or Canif, all kinds of filters. So yeah, we found similar stuff like zero harmonics, harmonics with some special numbers like two things close to each other. It's looks similar, but they are a little bit distorted, tilted to suit the data set better.
Sorry for so much question. So there was a challenge on Kaggle when they have these videos of your heart and
Yeah.
you need to predict the cancer. And I think that the winning team used RNN with convolutional neural networks and RNN for this time kind of sync. And is it like the same as you are doing, but in a slightly different way, or is it like a completely different?
Well, it's probably completely different because you can turn 4D. You gotta understand this module. It doesn't work only on 2D or 3D. It works on n spatial dimensions and m feature dimensions. So when you represent your information in n-dimensional form, it doesn't really matter. The only difference is that your spatial dimensions would be processed by convolutions, but your feature transformation would be multiplied by weight matrices like they usually do. So you can put in 5-dimensional information, but it doesn't probably not going to make a lot of sense because we don't have 5D imaging of anything. There also was experiments with activity recognition when people tried to. They had short snippets of videos, and they turned 2D video with time, and they rolled it out as a 3D tensor, and they used that to training. And essentially, one of the excesses was time, and it worked. Yeah, it did some like good numbers, but I haven't recreated that experiment yet. But it's not the best way to do that.
The answer would be that this is probably, like you're saying, that this is more, not high level, but general approach.
Yeah.
Okay.
But the only constraint, you got to have a sparse representation of your spatial data.
Yeah, I got it, yeah.
Thank you.
Okay. Thank you.